Good morning, ladies and gentlemen. Welcome to Get Going with GISMO. My name is James Stancombe. I'm the Programme Manager for GISMO at Lancaster University, and I'd like to thank you for joining the webinar this morning. The objective is to introduce you to the help that you can get from the GISMO project. GISMO, Greater Innovation in Smarter Materials Optimisation. It gives you fully funded access to the experts, specialist facilities and equipment at Lancaster University's Materials Science Institute to help you improve the way that you use, design and manufacture materials. And it's a project that runs until December 2022. So this morning, we're going to introduce the three technology themes behind the project to you, explain Lancaster's research areas and capabilities in those three themes. We'll show you how we think we can help you through the project. You'll have the opportunity to meet the team who will answer your questions. And to ask those questions, we'd like you to use the question box in front of you, and we will pick up on those right towards the end of the presentation. We're really excited to bring the project to you. We're convinced that it can do much to boost product development and process improvement in your business. But these are unusual times, aren't they? And in the midst of a pandemic. And we'd like to hear from you about your priorities and what would make the biggest difference to you right now to boost your ability to innovate. Again, if you would, please use the question box to tell us about those priorities, and we'll pick up on them in the course of the webinar and again at the end during the question and answer session. But first, what I'd like to do is hand over now to Professor Rob Short, who's the Director of the Materials Science Institute at Lancaster University, who's going to say a few words.
Good morning all. My name's Rob Short. I'm the Director of the Materials Science Institute at Lancaster University. And it's my great pleasure to welcome you to this GISMO event. I'm sorry that I can't actually be here with you in person. GISMO provides an exciting opportunity for my colleagues and I to engage with a broad range of manufacturers across the northwest of England. We're keen to engage with you, your material problems, and to find with you solutions to these problems. Our GISMO fellows are going to introduce our capabilities and capacities. So it's for me to, in brief, introduce you to the Materials Science Institute. Historically, Lancaster has had strengths in simulation and advanced characterization of materials, in two-dimensional materials and in quantum devices, in biomaterials and in the miniaturization of sensors, in energy and storage capture materials. In 2017, all of this was brought together under the umbrella of the Materials Science Institute. We're actively engaged in new interdisciplinary models of research and education in material science. And one of the raison d'etre for the Institute was to develop new models for working with industry. Together, principally, engineers, chemists and physicists, but we work with computer and data scientists, with designers, with biologists and medical researchers, and with social scientists. And we're supported by world-class facilities, which include, in the last decade, £20 million worth of investment in new analytical and manufacturing machines. And all of this is housed within inside £30 million worth of new bespoke award-winning buildings. And rather than read off a list, I invite you to visit our website. And finally, I hope you enjoy today and feel enthused to reach out to us. Thank you.
Thank you very much to Rob Short for that introduction to the Materials Science Institute. What I'd like to do now is move on to the three technology themes that underpin the GISMO project, as additive manufacturing, chemicals and hydrogen, and surfaces and coatings. The first to speak will be my colleague Armin, who will talk with you about additive manufacturing.
Thank you, James. Hello, everyone. My name is Armin. I'm working as an innovation fellow at Lancaster University. Here, I'm working with the companies to analyze industry problems, find the solution, and to develop a smart material that improve existing product. Prior to this project, I was working as a doctoral researcher in Lancaster University. My research interest covers a broad range of both academic and industrial interests, including multi-material joining technology for lightweighting, joint optimization, material characterization, and property measurement, failure and damage assessment, and additive manufacturing. In the next 10 minutes, I'm going to talk about engineering department capabilities, what we can do for businesses, and I'm going to show you an example of our previous work. Firstly, we are not new to this. We have been delivering additive manufacturing solutions to over 1,200 SMEs via the Lancaster Product Development Unit for nearly 20 years, much via ERDF funding. We have been constantly expanding our capability and staff aligned to these activities. Additive manufacturing, AM, also known as 3D printing, is a transformative approach to industrial production that can bring a digital flexibility and efficiency to manufacturing operations. Additive manufacturing method uses a data computer aided design CAD software or 3D object scanners to direct the hardware to deposit a material layer upon a layer in a precise geometric shapes. Additive manufacturing method is most often used for prototyping, and its ability to quickly manufacture a single part enables us to validate ideas in a cost-effective manner. We have state-of-the-art equipment in polymers like fused deposition method, fused filament fabrication, stereolithography or SLA, and selective laser sintering or SLS. We also have carbon fiber composite 3D printers and metal 3D printers such as selective laser melting or SLM and laser deposition welding LDM. We are going to be one of the first institutions in the UK to offer access to a novel dual material additive manufacturing process using a metal wire. This 3D printer uses a technology developed by Meltio, which is capable of manufacturing with metal powders or wires, or even combining both types of techniques on the same piece. The result is metal part with 100% density, a very attractive feature for industry as it increases the efficiency of parts. We have high-resolution 3D scanner based on blue light technology. It is perfect for capturing small objects or intricate details of large industrial objects in a high resolution with a steadfast accuracy and brilliant color, which is very useful for reverse engineering. We are also capable of using a traditional manufacturing method, CNC machining, and casting method to produce a prototype to support a AM technique. We can perform a wide variety of testing with industrial quality mechanical testing machines. This includes instrument machines with a different load cell that allows us to obtain a failure load accurately from a few newton up to 250 kilonewton. We have fixture to perform a tensile, compression, 3 and 4 point bending, and fracture toughness testing. We also have a 3-ball on a road rolling contact fatigue tester, which allows us to investigate a surface fatigue on a sample using a long-term testing. Digital image correlation, DIC, is another state-of-the-art piece of equipment in engineering department, which allows us to precisely measure displacement, strain, Poisson ratio, and also it can be used for observation of the crack and to create the 2D strain map in a specific area on a sample. We can potentially develop a bespoke test using a mechanical design software. Our in-house design team can design and build the fixtures and fitting to suit your samples and specimen, providing you with the best test setup to capture the data that you need. Also, we have industrial quality microscope, scanning electron microscopy or SEM analysis, provide high resolution imaging useful for evaluating the various materials for surface fractures, flows, contaminants, or corrosion. Through SEM and EDX analysis, we can provide a thorough examination of material properties and give a valuable insight to manufacturers. We recently added a new laser microscope, Olympus OLS 500, to our lab, with which we observe steps in the nanometer range and measure height differences at the submicron level. In addition, this machine allows us to measure surface roughness from linear to planar. We also have a methography lab to analyze the macroscopic structure of material to determine bark properties. This typically involves sectioning, mounting in various polymer systems, grinding and polishing to a mirror surface, chemical or electro etching of the surfaces, optical microscopy, and hardness testing. In engineering department, we have a wide variety of software. This include CAD and CAM software such as SolidWorks, AutoCAD, and CAMWork, which we can use for creation, modification, analysis, or optimization of your product. Also, we have license for a popular finite element analysis FEA and computational fluid dynamics CFD software such as ANSYS, Abacus, and COMSOL, which we can use during the product development process to predict what's going to happen when the product is used. In addition, we have thermodynamic and kinetic software, MatCalc and Thermocalc. These two software allows to compute phase equilibrium metallic alloys. This includes steel, stainless steel, magnesium alloys, titanium alloys, high entropy alloys, and aluminum alloys. Also, we develop in-house software for alloys and microstructure design. So now I'm going to talk about what we can do for businesses. We can help companies investigate additive manufacturing techniques for the first time by using our state-of-the-art equipment to produce a cost-effective prototype. Through a technology matching, demonstrations, test parts, validation, we can help a client to establish their own in-house capabilities. We offer additional expertise around modeling of a additive manufacturing process, modeling product performance as a part of design optimization, and conduct mechanical and physical testing to prove a new concept, design, or process, and overcome design or material issues. We are running a GISMO PhD specifically on improving functionality of part using a design for additive manufacturing principles. This will deliver a research outcome to partner aligned to this project via case studies, and we welcome industrial input to help to guide these projects. Now I'm going to show you one case study that we have done for a business line in the past. They are based in Carnforth. They manufacture a novel will-not safety device for commercial vehicles under the brand name Checkpoint. The majority of their products are currently sold to freight companies across the UK, but they were looking to increase their international presence. Business line had every faith in their wheel lockers devices, but required some more empirical evidence of the quality. They requested the help of the Lancaster team in the form of torque and tensile testing of their devices, and also of a set of competitor devices as a comparison. The test aimed to prove that the business line product is of a higher quality and should outperform their non-competitor devices. So Lancaster team performed a different type of testing. The torque testing was carried out using a torque transducer to measure the force required to rotate a nut held by the devices. The tensile test was performed using an industrial quality instrument testing machine to find the maximum failure load. While the nut and device were standard items, the fixtures to hold everything in a place needed to be manufactured, and it was a very specific size and shape, so we decided to model up a suitable fixture and use a selective laser sintering to make the fixture using a polymer 12 as the material. And finally, the test data gave a business line the confidence and the evidence to help them expand into international markets such as North America. Thank you so much for your interest and attention. If anyone would like some more information or has questions, please feel free to ask in question session or to contact me after the webinar. Now I'm going to hand over to Julian in Chemical and Hydrogen team.
Good morning, everyone. I'm Dr. Julian Dulce. I'm the GISMO Innovation Fellow responsible for the part Chemicals and Hydrogen in GISMO. And just to let you know, my background is set in synthetic organic chemistry. And as we're going to see, this is going to be a recurring theme in this presentation on chemicals and hydrogen. So first, brief introduction on this theme, chemicals and hydrogen, which can seem a little bit vague. Hydrogen itself is fairly self-explanatory, but chemicals is rather vague. And considering GISMO is an acronym short for Smarter Materials, when mentioning chemicals, what comes to the mind of an organic chemist related to materials is polymers. So here are some graphs that are just picked from the web, just showing the world production of plastics and hydrogen both in the millions of tons, therefore really highlighting the potential, the great potential even should I say, for research that they both offer. Why synthetic organic chemistry, you might ask? Well, this is a good question, and as it is my area of expertise, I will try to demonstrate its value by explaining how it links to all areas of chemistry and even to other fields of science. A synthetic organic chemist uses tools to serve the purposes of research areas that reach a broader scope than simple chemistry. Here is a selection of tools essential to organic chemists and relevant to the GISMO Chemicals and Hydrogen project. First, there is Catalysis. Then comes Analytical Chemistry, and finally Physical, Organic and Computational Chemistry. These three themes work in synergy to allow the synthetic chemist to make and design molecules useful in fields such as biology and medicinal chemistry, material sciences, or even green and sustainable chemistry. Now I will go over each of these elements individually, more in detail, explaining how each of these aspects fits with GISMO, and in particular chemicals and hydrogen, and also giving you examples where we've been working with industrial partners. Starting with materials, which I suppose is the most obvious theme of GISMO. As mentioned previously, materials for synthetic organic chemists means polymers. And regarding polymers, several aspects that relate to organic chemistry can be considered, starting with polymer synthesis. For polymer synthesis, you take a small molecule called a monomer, you react all these monomers together, you obtain larger molecules, that's the polymer. And the properties of this polymer depend both on the reaction conditions used as well as the type of monomer. This also means that if you want to change the properties of your polymer, you will have to redo the synthesis every time, which can be an inconvenience when you want to optimize the properties of your polymer. An emerging approach and a solution to this is post-polymerization functionalization, in which you take a non-bulk polymer that you can functionalize after polymerization. You can functionalize it in various ways, and this way tune the properties that suit your requirements. Both of these approaches require method optimization. I'm putting it out there, although it might seem a little bit out of the way, but this will relate later with the physical organic chemistry part of the presentation. And this method optimization will have the aim of obtaining efficient and tunable grafting and tagging of the material with a small molecule. Regarding collaboration with industry, we've been working on the synthesis of biodegradable polymers for disposable coffee and teacups, and we're currently working on the post-polymerization functionalization of polyisoprene as a mean to modify the properties of the polymer. Falling under GISMO scope would be, for example, the functionalization of polymers with stimuli responsive tags or biologically active molecules. A little bit more on post-polymerization functionalization. I just want to show you a figure picked from a publication from 2017, which depicts the future of polymer functionalization as either the synthesis of novel polymers bearing handles that can be functionalized selectively, or the use of well-known polymers like polystyrene, for example, or in my example previously, polyisoprene, that you would react in novel ways in order to introduce functional groups onto them that modifies the properties of the polymer and suits the application you desire. Now moving to green and sustainable chemistry. Well, this is definitely a key theme of chemistry for the future, and therefore represents significant research opportunities. For this, synthetic organic chemists are looking to develop environmentally friendlier reaction conditions using either renewable feedstocks or valorizing waste. All of this in the aim to improve the overall sustainability of chemical processes. Regarding previous experience with industry in this field, we've been working, for example, on the purification of waxes obtained from the pyrolysis of plastic waste, and linking this with GISMO, a perfect example will be the valorization of hydrogen waste stream. Now moving on to biology and medicinal chemistry. At first glance, this could seem a little bit remote from GISMO's theme. However, thinking this would probably be wrong, and I'll try to show you why. Synthetic organic chemistry related to biology and medicinal chemistry generally means small molecule synthesis, which requires method optimization. You can see this method optimization is popping up again. It's like a recurring theme of every single aspect of organic chemistry, and you will see how it links to the part of the presentation later. Once optimized reaction conditions are obtained, libraries of drug-like molecules can be synthesized and biological testing can be performed. Our experience with industrial partners in this area relates to the synthesis of a library of drug-like compounds, which actually has been done using a method developed in our research group. Relating to GISMO, this could mean using hydrogen waste for the synthesis of small molecules, or even grafting small biologically active molecules to polymers or other materials. Right, now let's go over the items that are depicted as synthetic organic chemistry tools. First comes Catalysis, where it is essential for improvement and optimization of known chemical transformations, and can link to the design of new reactions and the synthesis of novel compounds. For this, robotics and high-throughput screening have become a modern tool and will soon be available to us at Lancaster University. My experience with Catalysis includes publications of patents and papers showing the potential for added IP value, which is non-negligible. The link tying Catalysis to industrial partners was already mentioned in this presentation with the synthesis of drug-like compounds, and falling under GISMO's scope, can be, for example, the use of hydrogen for catalytic processes or for polymer modification. Moving to analytical chemistry, well, let's start by stressing that analytical chemistry is essential for all synthetic chemistry to be carried out efficiently, starting with compound purification using chromatography, HPLC and GC. Then comes compound characterization and quality control, for which several tools are available at Lancaster University, ranging from techniques used routinely by organic chemists like NMR or mass spectrometry, to techniques more relevant to material sciences like microscopy and X-ray, and to polymer-relevant tools like DSC and size exclusion chromatography, and not forgetting elemental analysis, which is a useful tool to characterize impurities. My experience combining analytical chemistry and industrial partners is the pyrolysis wax project mentioned earlier, which fits perfectly with purification and quality control. Finally, last but not least, and perhaps the most abstract tool I've listed here, physical organic and computational chemistry. This is relevant to reaction optimization, really, which you have seen in this presentation is a central theme running through synthetic organic chemistry. The mechanistic studies provided by physical organic chemists and computational chemists allow for better understanding of chemical transformations. In some cases, the use of machine learning to analyze large datasets have shown that they can allow for efficient prediction of the outcome of chemical reactions. And while I'm not proposing that this is something we're going to get deeply involved in GISMO, I thought it was useful to highlight that reaction optimization is not just a black box. Things exist that make it happen efficiently, some of which can and will be used for the optimization of chemical transformations performed under the scope of GISMO. Now let's have a summary of what I've mentioned in this presentation, revolving around synthetic organic chemistry and the chemicals and hydrogen theme of GISMO. 1. Post-polymerization functionalization. 2. Use of hydrogen waste stream for improved sustainability. 3. Use of hydrogen for small molecule synthesis. 4. Use of catalysis in transformations involving hydrogen. 5. Use of modern physical organic tools for reaction optimization. And 6. Use of the analytical suite available at Lancaster University for compound characterization. In other words, we can help you to develop and validate new materials, products and processes, improve process control, scale up or reorganize your production, create new molecules, formulas or compositions, understand the latest thinking and techniques. Thank you for your attention, and I'll be happy to answer any of your questions regarding the chemistry and hydrogen theme of GISMO. And now I'm going to hand over to Alex for the surface and coating aspect of the project.
Hello, I'm Alex Robson, and as you might expect by this point, I'm the third Innovation Fellow working on the GISMO project. It's my role to act as a point of contact to liaise with companies, with academics, our wider project team, to help diagnose problems and challenges, to identify where we can support businesses, where we can apply our research, where we can form collaborations, and also to develop and deliver projects, whether that's in the lab myself or by supporting others. And my specific role is on the surface and coatings theme, and that aligns closely with my background in materials analysis, in surface science and coating development. I've been involved with surface analysis techniques, predominantly scanning probe microscopy, but also a range of others, for approximately 12 years now, across a wide range of material systems, from biological materials through semiconductor devices, through to thin films, And I've also been involved with the development of coatings using various different techniques. Currently, a lot of my research work involves developing coatings using plasma polymerization. The surface and coatings theme itself is interdisciplinary. There are members of Lancaster University's physics, chemistry and engineering departments within the theme, and it ties in very neatly with the Materials Science Institute, which is active in interdisciplinary research, development and education around new materials science. So as to surface and coatings themselves, well, with surfaces, as I expect everyone here is aware, we're talking about the outermost layer or region of a material, a product or a device, where it's interacting with its surroundings and its environment. The actual properties and behaviour of a surface, of a thin film or a layer, can be very different to those of the bulk of the material or a product or a device, and they can greatly affect the material's behaviour. And you can also exploit those properties to provide some form of functionality to a material. Correspondingly, surface analysis techniques can provide a great deal of information about a sample or a product, as surface interfaces are critically important in how a material is interacting with surroundings or other materials. Information about a surface's structure or chemistry can be key for things such as quality control, for problem solving, for product or process development. Examples could be things like verifying the structure of a device or a product, such as maybe a semiconductor LED or a laser or something like that. Identifying contaminants or impurities on a sample, determining the composition of something like a thin film, characterizing surface, material and device properties, and also identifying differences between different materials from different suppliers and so on. So things similar to this. The other part of our theme focuses on coatings. So surface coating in general is an effective, proven industrial route to add substantial value to existing materials and products. And it's getting increasingly rare these days to find a product where there hasn't been some kind of thought as to how it's going to interact with its environment, whether it needs some kind of surface modification or coating to help it achieve its intended purpose. And surface coatings can enhance multiple material properties. You might be looking at enhancing performance or reliability, versatility. So maybe if you want to use something in a different context to its original form, or things like also enhancing endurance. These properties can also include things such as maybe enhancing the hydrophobicity of a material, or looking at anti-fouling behaviour, antimicrobial or antiviral behaviour, which is obviously a very pressing issue at the moment. But it could also be things like exploiting optical properties of materials, looking at enhancing or giving different thermal and electrical behaviour, changing adhesive properties for things like biocompatibility and so on. And functional coatings in general are applied to a wide, diverse range of products and markets, from things from contact lenses through to drinks cartons. They're found in automotive products, textiles, polymer films, construction materials, products or processes that might be affected by biofilms, so bacteria buildup. So that might be things like pipes and medical implants. So given all of this, so how can we help on GISMO? What kind of problems can we solve within the surface and coatings theme? Well, we can do things like helping to develop and optimize new functional coatings, functionalized surfaces for products and materials. We could undertake proof of concept studies, prototyping, maybe demonstrating feasibility of ideas, trialing processes that might help you inform decisions as to whether you want to go in for large-scale production down the line. We can help analyze and characterize materials and surfaces. We could help identify contaminants. We can look at aiding with identification of issues and processes and helping you to come towards solutions for those things. And I would like to think that we could help understand the latest thinking in these areas as well. And one thing I do want to highlight as well is, similar to our other themes, we have a number of graduate researchers who are going to be working on research projects within the GISMO framework as well, and we hope that businesses will engage with these. Broadly, these are the development of surfaces in the fight against antimicrobial resistance, development of plasma-based coating techniques for atomically precise materials, for molecular materials, and development of scalable methods for the functionalization of 2D materials. So that would be materials similar to graphene, for example, for quantum security and green energy applications. So if there's anything in there that's of interest to businesses, please do get in touch, and we'd be delighted to see how we could work together around this. If it sounds like a confusing medley of words, we'd be very happy to run through things in much more detail and discuss how any of that could relate to your business at another point. So to give you an idea of some of the project examples that we've worked on in the past, I have a couple of quick case studies here. I'm afraid I can't give you full details just because of the agreements that we have in place, but these should give you an idea of the kind of work we could potentially do. And the first of these involved the development of a patented hydrophobic coating for a product for a scientific equipment company. Here they wanted to improve one of their products to help guide sample preparation for a particular system and a particular process. And this project involved us working across our physics and chemistry departments to identify suitable coating and patterning methods, the practicalities of doing that, a review of existing literature to guide and identify suitable chemistry to use, surface analysis of materials and products, development of protocols to optimize the coating process, and testing of the prototype coatings themselves at the company's headquarters. So on the surface analysis side of things, we performed some microscopy, some compositional analysis, compositional mapping, some contact angle measurements, basically to establish how hydrophobic the materials were. And we also looked at some competitors' products that we've been provided, which allowed us to establish a benchmark of what we'd ideally like, and gave us a point of reference for making our own prototype coatings, essentially allowing us to know what we needed to aim for. And that led us to being able to produce some initial prototype coatings using one of our plasma polymerization reactors, which you can see here. Essentially, the product is immersed within the plasma and the exposed surfaces are coated. And that's the glowing tube region on the picture there. And using plasma processes and masking techniques, we could produce a prototype for the company, which we then tested in our own labs in the same way as before. So looking at composition, looking at hydrophobicity, that kind of thing. And then we passed a prototype, or a series of prototypes rather, to the company for testing in their in-house lab using real-world methods. So essentially what would be done by consumers down the line. And we're currently undertaking a second round of optimization to tweak the processes so the company can hopefully look towards scale up and ultimately market these materials later on. The second case study is a materials analysis one. This involved a manufacturer making a range of coatings. This was a situation where we actually had a much broader discussion with the company about problems they had, how we could help, and also one of the issues that they came up with was that they had suspicions that a particular coating wasn't working perfectly due to a reaction between the substrate that they had and the coating itself. But they didn't actually have conclusive proof of this. They didn't have an observation of that. And they provided us with a number of coated samples, so different substrates, different coatings. The particular example here that I have is a coating on glass. And our approach was to lean on the expertise that we have in our physics department around microscopy and cross-sectional analysis. And in this case, we used scanning probe methods to analyze the surface topography, its electrical and thermal behavior, both on the actual surface of the sample to see if we could see any effects coming through the coating from below, but also in cross-section, which we produced by milling the sample with an argon ion beam. You can kind of think of this a bit like atomic sandblasting. Essentially, you expose part of a material to the ion beam, it mills it away, and you end up with a smooth surface which you can then put into a microscope or a different piece of analytical equipment and look at the internal structure. And again, we used scanning probe techniques here, looked at the topography of that cross-section, looked at its electrical and thermal behaviour. And the striking feature that we observed straight away was there were a number of holes, or I guess almost pockets, lined along the boundary between the substrate and the coating itself, which are highlighted on the picture with red circles. And the identification of those defects, those holes very neatly fitted in with the company's suspicions, basically allowed them to confirm that they did have an issue, and then look to modifying their processes to try and engineer that issue out. So hopefully that gives you some idea as to how we can help businesses in the surface and coating sphere, and the case studies would hopefully give you an idea on how we might approach a particular problem or issue. And now I'm going to hand back over to James again. Thank you.
Thank you to Armin, Julian and Alex for their detailed insights to the 3 technology themes covered by GISMO and the expertise, equipment and facilities that Lancaster University can bring to bear to help you. But what kind of help can you get and how does it work? Let's look at each of these areas in turn. The most important point for us to make here is that the support is tailored to your needs. By no means is it one size fits all. You've heard already from our 3 Innovation Fellows about the projects we've undertaken with businesses, and you'll have probably noticed that they vary in depth and duration and the level of resources required. And as you heard from them just now, it is the role of the Innovation Fellows to understand the problem, understand the issues around it, perhaps do some initial diagnosis with you, agree an action plan, and then coordinate the resources required from within the university, whether it needs a couple of days, a couple of weeks, a couple of months, or even longer, to deliver a solution that meets your needs. If you have a project in mind, if you've been working on a problem that you need some help with, or you just want to put your products to the test, do get in touch with us. We'll show you how to do that shortly. GISMO is also sponsoring a number of graduate research projects in the university on areas of material science with ramifications for future product development and for the economy in general. You've heard about some of them earlier, and here's the full list. If there's anything there of interest to you and you'd like to contribute or be kept informed of the research's findings, please do get in touch with us. In any event, we'll be giving the researchers a platform to discuss their projects through GISMO's web and social media platforms and through news releases, so stay tuned. Another source of help that always proves popular with businesses are student interns, funded by the project to undertake projects for you. These bright minds can help you to solve a problem, trial a role, or research a new idea. You define the project or problem that you'd like to solve, and you get to interview the candidates from within the university that come forward and select the one that you would like to work with. In this way, you get access to expertise from across Lancaster University's science and technology disciplines. Again, depending on the nature of the project, it could be anything from 2 weeks to a year, and it could be part-time or full-time. Now, if you've got a project in mind, you'd like some help in that way, do get in touch. Get in touch. If you'd like to keep up with GISMO and what's going on within the project, do get social with us. Follow us on Twitter, subscribe to our e-newsletter through the website, and if what we've talked about today has been of interest and you have a project in mind or you'd like to discuss something with us, do get in touch. Email us at gizmo@lancaster.ac.uk or call us on 01524 510 464. But I'd be very grateful if you could leave it until 5 minutes after the webinar before you make the call, so I could at least make a brew. And on the subject of getting in touch and keeping in touch, we hope that you'll join us again in a few weeks' time when we hold the first in a series of breakfast seminars on developments in material science. On 13th of October, Professor Rob Short will be discussing developments in surface coatings, and we'll cover how to improve the reliability and performance of coatings and your products, and particularly their antimicrobial and antiviral properties. And then on 27th of November, Alex Robson will be expanding on his earlier presentation to talk about the latest developments in surface analysis and how to use surface analysis to improve your materials, products and processes. Go to the link shown to book your place. Book early to avoid disappointment. GISMO isn't the only project being delivered by Lancaster University to help businesses like you in the Cheshire and Warrington area. There are a couple of others which, like GISMO, are part funded by the European Regional Development Fund, but unlike GISMO, these two are actually delivered in conjunction with other universities across the northwest of England. EcoI Northwest is all about delivering low-carbon business innovation through collaborative PhD projects between the business and a university. It's a great way to access the equipment, expertise and resources of those universities. Whilst the Greater Manchester Cyber Foundry project can help you with innovations in digital and cyber technologies, and that's being delivered by a combination of online workshops and one-to-one support. If you'd like to find out more about those projects, visit the links that you can see on the screen now.